All right, let's dive in and get back on track. Uh, We're going to go back to looking at something we saw way back in 2301. So a little break from spectroscopy and still another break from reactions. Don't worry, we'll get back to reactions. But now we're going to look back again at molecular orbitals. So this is chapter 14, which is actually a revisiting of chapter 3 when we first started looking at molecular orbitals. What's different? Well, now we're looking at molecular orbitals that are not just localized on two adjacent atoms. They actually spread out across a whole slew of atoms. It's very useful for understanding reactivity, and a big part of chapter 14 is understanding the concept of aromaticity. This mini lecture will focus on just the earlier parts of chapter 14. So that is this concept of multiple center MOs, and all that means is that when you have atomic orbitals on adjacent atoms, like more than two, like maybe even 4 or 5 or 6, those adjacent atomic orbitals can all interact simultaneously to make one gigantor molecular orbital, aka a multiple center MO. But why is this important? Well, because, as usual, it explains things when our other theories fail. So, back in the day, I think this was chapter 11, we looked at electrophilic addition to conjugated alkenes. So, for example, if we added bromine to this, conjugated cyclopentadiene, yeeks, we get a mixture of products, showing us that we get a mixture of both the 1,2 and the 1,4 product. How do you explain that? That's kind of weird. And worse yet, how do you explain this? That when I add bromine to this conjugated alkene, looks pretty conjugated to me, nothing happens. You don't get 1,2, you don't get 1,4, you don't get anything. So how do you explain all this? Well, how you don't explain it is by valence bond theory, because valence bond theory fails us here. We've seen already that Lewis structures are really nice and simple and clean and straightforward, but they just don't explain everything. So then we turn to resonance. If we look at drawing those pretty little electron movement arrows and delocalizing the electron density, boy, that explains a lot of stuff. But it still doesn't really explain things in terms of molecular orbitals. And when we have been thinking about molecular orbitals, we're not really able to extend them to these systems that have more than 2 atoms in them. So what's the deal here? We're going to explain this concept of multiple center MOs by taking a very detailed look at one system, that being the allyl cation. So here's our picture of the allyl cation in kind of our basic mode, back when we said, okay, so this thing, this allyl cation, which is H, dot, dot, dot. This is what we're talking about. Well, we know what that looks like. It's got a pi molecular orbital here, and, that's sp2 hybridized, so there you go. But that doesn't make sense. Because, I know I can draw, I can do resonance delocalization to get me to this resonance contributor. But, how frustrating. What does this thing really look like in terms of molecular orbitals? Like, it can't be flipping back and forth like that. So what does the hybrid look like in terms of molecular orbitals? What's the highest occupied molecular orbital for this thing? We know that's how reactions take place. What's the LUMO for this thing? We're going to pull it all together by constructing a molecular orbital energy diagram as shown. All right, first we look at the allyl cation, and we see that it has many molecular orbitals. After all, what is a molecular orbital but the overlapping of 2 atomic orbitals to make a bond? So for each bond we have a molecular orbital. Gee whiz, there's a lot of bonds in this thing. In fact, if I start thinking about it, in the allyl cation system I have lots of electrons, 16 electrons total, when you're considering all of my sigma bonds and all of my pi bonds. Well, the good news is we get to ignore most of those molecular orbitals and ignore most of those electrons because we're only interested in the pi system. Okay? We're only interested in the system that involves those three adjacent p orbitals. And if you think about that, you can see that, of course, that means we're only looking at 2 electrons because that guy is empty and this guy has 2 electrons. All right, so let's start constructing our molecular orbitals. If we're talking about 3 atomic orbitals, those 3 p atomic orbitals, that means we have to have 3 pi molecular orbitals. Remember, there's a conservation of orbitals. The number of atomic orbitals has to equal the number of molecular orbitals. Okay? So there's 2 other rules as we draw or construct our molecular orbitals. We need to make sure they remain symmetric, and when we put our electrons into our molecular orbitals, we always start at the lower energy molecular orbital first. All right, let's just do this. Let's do this thing. Here is a little bit of an energy diagram showing you 3 different energy levels because we're going to have 3 molecular orbitals. I mean, we can just call them, if you want, we can call it psi 1, psi 2, psi 3. So that's representing my 3 molecular orbitals. What do they look like? All right, well, let's think about this. If I have 3 adjacent p orbitals, certainly the most stable one would be completely bonding. All 3 orbitals would be in phase, and they could all overlap, and that's what I think my lowest energy molecular orbital should look like. And that would be good because that is what my lowest energy molecular orbital looks like. It looks just like that. So totally symmetrical and totally distributed evenly, top and bottom, across the 3 carbons. There is a nodal plane right in the same plane as the carbons and hydrogens, so this guy has 1 node. Well, we know we only have 2 electrons, 2 pi electrons, so there they are. So that means this must be my highest occupied molecular orbital because I don't have any more electrons to put in there. All right, well, that's pretty easy. That's what the lowest energy orbital should look like. And actually, the highest energy orbital should be pretty easy to figure out too. You know, basically, again, we're talking about having these 3 p orbitals. And now, if they are completely anti-bonding, then we can't overlap anywhere. We've got 3 nodes. And indeed, that is what our highest energy orbital looks like. Now, it's not the HOMO. The HOMO is the highest occupied molecular orbital. This was just the highest energy molecular orbital. And there you can see node, node, node. Cool. So what about this middle energy molecular orbital? That's a bit more tricky, right? Because I have 3 carbons, but somehow or other I have to get 2 nodes, and it still has to be symmetric. Well, I'm just going to skip ahead and show you what this thing looks like, because it's kind of wild. And for those of you who are chemistry majors, you'll get to understand this in droves once you get to PChem. So basically, this is my middle, my psi 2, my middle molecular orbital. What you can see is I have that kind of molecular orbital on the left and opposite phase on the right, but I got nothing, honey, and that's not going to work, in the middle. Okay, there it is. No node, no molecular orbital in the middle. That's the only way I can have my psi 2. So that's what psi 2 looks like. And that means it would be my LUMO. So here it is, and there's just nothing there. And that's my LUMO. Okay, does it make sense? Heck no, it's quantum mechanics. It's the Schrodinger equation. But trust me, that's what the middle molecular orbital looks like. All right, so moving right along. That is our molecular orbital diagram for the allyl cation. The next question is, can you take it away from here and do the same sort of exercise, but instead of the allyl cation, you would draw the MO diagram for the allyl anion, or for that matter, the allyl radical. Keep in mind, the only thing that's going to be changing is the number of pi electrons in the system. So take it away. I suggest that you do that exercise. All right, that is it for this intro. We have to end up with a terribly amusing joke, which simply is, what did Obi-Wan say to Luke at the Chinese restaurant? Use the forks, Luke. Get it? Yeah, okay. All right. See you in class.